Good evening, everybody. Nice to see you all. Haven't been here for a couple of months for various reasons, but very nice to be back and nice to see you all. Welcome. Who's anybody who visits their first time to see? Well, welcome. There's quite a few of the committee here. Committee can stand up. So you're sitting next to the committee. So introduce yourself to the committee, and they'll be happy to talk to you. Thank you. So this evening, the agenda. We've got Professor Stephen Wilkins here, who's going to talk to you about the end of the Dark Ages. So people that start up within bang after it started to stars and make up the problem. We'll tell you all about that. Stephen is at Durham, went on to do a master's PhD in Cambridge, then went to Oxford, and then is now head of one at Sussex University. And I'm sure it'll be a fascinating talk because he's telling me he's done a mixture of started off as an observer, then went through simulation, now he sits somewhere between the two. After lunch, after that, we're going to have coffee, and then we're going to have Rachel talk about outreach, not out to teach. I think it's very important. Outreach, and then after that, Richard's going to tell you a little bit about some of the work that we're doing on JWST and some of the things we've been learning about that. And then I can actually give you an update on the charity. We have actually had some response on the charity. And then if anybody's got anything else to raise, we can discuss that with you. So with that, I'll pass you over to Stephen, and I'll just stop sharing this.
Okay, thanks everybody. It's actually been a few years since I've visited Surrey, despite the fact that I'm relatively close, really just down the road. And I think it's just because of the awkward train lines. So I actually came early today. I managed to take part in one of the celebrations at the university today. I've actually known some of the faculty here for about 20 years, which is kind of scary to think about ever since I started my PhD. So I managed to give a seminar to the research group. And then I heard there's been some, some distressing news on campus, but I think that's all sorted out now. Well, let me just outline my talk. What is that? Let's see if this is going to work. Okay. So a little bit of an outline of what I'm going to talk about today. So I'm going to talk a little bit about myself, first of all. And then I'm going to talk about my team, because all of the research that I do is only really enabled because of teams both at Sussex and here in the UK, but also, really across the world. And this is one of the great things about astronomy, because we end up collaborating with people all over the world, right? There are really very few barriers to astronomy. And I always make the point that's pretty much because astronomy is useless, or at least it's not commercially sensitive in most cases. Obviously, some aspects of hardware design are, but the things that I'm going to be talking about is very blue sky science. So it's very fundamental. It's all about how we can explore our universe. So I'll talk about the team, I'll talk about the big picture. So what are the things that we're trying to answer? I'll then go on to the early universe, which is really just an introduction to the early universe, which is the main topic of my talk. And then I'll talk about how we can observe the early universe, and then move on to how we can actually simulate the early universe. So I actually work at the interface of both observing the universe and trying to simulate the universe, so trying to model it. Okay, and that's somewhat unique. So a little bit about myself. So my northern accent is disappearing, but I think it's still there just about, right? Particularly if I've had a drink, I become, people can't understand me anymore. And actually, I've had like 3 beers today, so good luck. Fact, my interest in astronomy was actually first driven by playing a computer game. And this was a game called Frontier Elite 2 in the mid-1990s. So you can work out exactly how old I am from this fact. I'm too young to have played the original Elite, right? I'm now kind of too old to play the new version of Elite because I don't have time anymore. For anybody who doesn't know what Elite was, it was this seminal space simulator where you could do anything that you wanted. But what was really great about this is that the developers of the game actually embedded a whole load of actual real-world physics into the game. They put a lot of care into that. So for example, they're obeying Newtonian dynamics in space. So it was very different from, traditional space shoot-em-ups. But one thing that really, caught my attention in those formative years was that they really cared about actually building a realistic universe. So they built entire star systems. In fact, they built hundreds of billions of star systems, right? And these were just stars, but they also had planetary systems. And this is really amazing because at the time, we only knew of planets around the sun. We didn't know that the universe contained all of these other planets that we've now subsequently discovered. So they imagined all of these different star systems, and you could visit the individual planets and the moons, etc. Over here, you're just seeing their representation of our own solar system, but you could see this kind of thing for lots of different solar systems. And they had actual real stars in the game, but then they also had some procedural generation, and they actually told you like the actual characteristics of the star, right? And as a quite nerdy teenager, this really caught my attention, and it's one of the reasons why I went into the field. This is what the game looks like today. So this is now Elite Dangerous, and anybody who has spare time, I encourage you to play it. It is about 10 years old now, but it's still really, really cool. You can go like explore black holes and things. Seeing lots of nods in the audience. Obviously, I've chosen the right demographic. What happened next was, as mentioned, I went to Durham, I went to Cambridge, went to Oxford briefly, and then I've been at Sussex now for 13 years, working my way up the academic hierarchy. As I've gone this way, my blood pressure has also gone in the same direction. So I'm actually, honestly, really badly hypertensive. It's no joke. Especially now that I'm head of physics and astronomy, which it's really not a very good time at Sussex and nationally to be in this position. So please pity me, which is why I've had several beers today. Anyway, as I mentioned, all the work that I'm going to talk about today is really only enabled by a team of wonderful people that I surround myself with. This was from a few years ago now, but it's a nice picture because I still look relatively young. This was actually at a festival before the James Webb Space Telescope launched, telling people about it. And then a few pictures from more recently from the last couple of years. And then my colleague, Peter Thomas, who sadly died now just under 2 years ago, who was one of my closest collaborators at Sussex. But all of the stuff I'm going to talk about is really only enabled by these people. And it's not just these people, these are my local team, my local collaborators. I work with people all over the world. Okay, and this is earlier, wow, what's going on? Okay, earlier in the year, I managed to organize a conference in India. It's a country that I've always wanted to go visit. So I thought, I'll just organize a conference there and I get to go. So that was great. And while wandering around, we found this supermarket. And so there's a bunch of my international collaborators here at the Galaxies supermarket in Kerala, in India. Oops. And this was us visiting a tea plantation. We were working, we weren't just doing tourism, but if you're going to fly halfway across the world, you may as well do some. Okay, so starting off with the big picture, where you always should. This is horrible. What's doing this? So fundamentally, as scientists, what we're trying to answer is, how does everything work? Right now, no one individual or even team could really answer how does everything work. And so we can break this question down into smaller questions. This is horrible. Why is it doing this? So, when we talk about astronomy and cosmology, what we're trying to answer is, well, how does everything work, but on the largest scales, right? So how does the universe evolve? How do galaxies form and evolve? But again, even that is too big a question for any one individual or even team to answer. So then what we really try to answer is, well, how do galaxies form and evolve? Right, so this is a more specific question now. And we often call this extragalactic astronomy. And again, an individual can't solve this. But what an individual can make progress on is these smaller questions. And these are some of the smaller questions that I'm hoping to answer with my research. So for example, how, when, and where did the first stars form? How, when, and where did the first supermassive black holes form? And what impact do they have on their surroundings? Right, these are things that we know exist. How are the chemical elements created and dispersed? We know when the universe was first born, it was chemically very, very simple. It was just hydrogen and helium. And it was through stars living and dying over the next, few billion years that we create a rich chemistry which enables life today. And then many other questions as well, many smaller questions. But the point is that these questions are actually tractable for individuals or small teams to actually eventually solve. Okay. So to give you some more background, I'm going to talk about the early universe. So this was really the first stages of our universe's history. So, for moving on to 100 years now, we've known that our universe is expanding. This is the hot Big Bang theory. And a consequence of this is that as we look back in time, the universe was different. It changed over time. And specifically, as we look back in time, the universe gets denser, it gets hotter, right? But that actually also implies that the universe has a finite age, right? Our universe has only been around a certain amount of time, right? And that amount of time is, roughly 14 billion years, plus or minus a few 100 million years. Okay. And so actually, if you extrapolate, if you extrapolate our universe today to back when it was all together, right, this is what we call the singularity, or the hot Big Bang. Okay. And so we think the universe emerged from this singularity, roughly 14 billion years ago. Now, this seems very abstract, but we're actually able to observationally probe the evolution of our universe because of a quirk of our universe. And that quirk is that light takes a certain amount of time to travel through the universe. So as I look at you, I'm seeing you as you appeared a fraction of a second ago, not as you are right now, right? And on astronomical scales, this becomes a larger and larger number. So for example, when we see the moon, we're actually seeing it as appeared about a second and a half ago. The nearest star, this is the Alpha Centauri system, which is actually 3 stars. The light has taken about 4 years to reach us. The Southern Ring Nebula over here, about 2,500 years. I would say should be everyone's favorite image in astronomy, the Pillars of Creation, made famous by Hubble, but this is from Webb. We're seeing this structure as it was about 6,000 years ago. So this is now, almost human recorded history when this light was first emitted. Oops. Really, really sensitive control. The nearest galaxy to us, so this is the SMC, the Small Magellanic Cloud, 150,000 years. Andromeda, 2.5 million years. It's ruined the joke. Everyone's favorite galaxy, ARP 142, obviously because it looks like a penguin, right? It even has an egg. I mean, just look how eerie this is. Actually, this makes a really, interesting point. The reason why we see galaxies that look like penguins is presumably not because the creator favors penguin-shaped things. It's really a consequence of the fact that our universe contains huge numbers of galaxies, between 100 billion and 1 trillion. So if you look at enough of them, you're going to find some that look like penguins and other things. Okay, so it's actually a quite interesting point. It's really annoying. This remote control ruins it. Okay, and then the most distant galaxies that we can find, and these are the things that I'm going to talk about today, we're now able to see individual objects when the universe was around 13.5 billion years old, right? So we've now covered the vast majority of the universe's history, right? That doesn't mean I've been able to see everything across the universe's history, but in certain directions, I've been able to see galaxies which were potentially forming the first generations of stars. And then actually, you can look a little bit further. We can actually see this leftover light from the Big Bang. This is the cosmic microwave background radiation. We've been able to detect this for around 70 years now, but this is light basically emitted when the universe was really, really quite young. And it's got a whole lot of information in here as well. Okay, so going back to the really early universe now, we know a few interesting things happened at the beginning. And one of these interesting things was something called baryogenesis. And this was, as the universe expanded and cooled, energy was essentially turned into matter, right, or baryons. Right, and this left our universe mostly composed of matter in the form of subatomic particles and radiation. And actually, a few minutes later, and I like this because it really was, it's something like 8 minutes later after the Big Bang, right, we created the first chemistry. We created hydrogen and helium, or the universe created hydrogen and helium. And then it kind of stayed this way for the next couple of 100 million years, right, in terms of the chemistry. Now, during this really early universe, roughly encompassing the next 400,000 years, the universe was really quite foggy, right? And that's because all of the gas in the universe was ionized. All of the electrons were stripped from the nuclei. And what that means is that light can't travel very far without being scattered in another direction. So this is analogous to actual fog here on the Earth, where you actually have water droplets scattering light. It's a nice picture of Brighton Pier over here, but you can see, you can't see very much of it because of the fog. Now, as the universe expanded and cooled, eventually these three electrons and atomic nuclei, they combine together, right? And it's at that point that we can start seeing the universe. The universe becomes transparent. Okay, and so that's when we see this cosmic microwave background radiation. So before this, the universe was essentially too foggy. We can't see before this. And this is essentially the face of the cloud or the fog. Okay. As the universe expanded, this cosmic microwave background, this cosmic background radiation, which you would have originally been able to see with your own eyes if you were there, gets shifted to longer and longer wavelengths, right? All the way to today, it's shifted into the microwave, which is why we need radio antennas to discover it. And so what we then say is that the universe entered what we call the cosmological dark ages, right? So this is when there were no other sources of light in our universe. So when we say dark ages, we don't mean this. Bonus points if you get the cultural reference. Again, right demographic. Oh, it's ruining it again. This dark ages. So not this dark ages, this dark ages. So the period of the universe's history where it was literally dark. Okay. Oh, I'm just going to give up. Okay. So although this, roughly 100 million years or so, we call it the cosmological dark ages, that's not to say that nothing was happening. During this time, what's actually happening is that gravity is pulling material together. So although the universe is expanding on large scales, what's actually happening is that gravity is pulling things together on these small scales. Right? So we're seeing this growth of structures. And I'll show you a video of this later. Now, eventually, you pull enough stuff together that your gas can cool and become dense enough that it can trigger star formation. So at some point, we have the formation of the first galaxies and the first stars. So this is a real image, but it's not a real image of one of these first galaxies. It's actually a relatively nearby galaxy. But this is the type of galaxy that we expect to form first of all. So it's very chaotic. It's relatively small. Right? This is what we think the first galaxies probably looked like if we were sufficiently close to them. Okay. Around the same time, we're going to form the first supermassive black holes as well. Okay. So that's the kind of overview of what's going on here. So just to outline some more of the open questions, the things that we're trying to answer by studying this period of the universe's history. So the things we don't know at the moment are, for example, how did the first supermassive black holes form? What was the source of photons responsible for this process called reionization? This is not something that I've talked about at the moment, but I'll try and talk about it later. Were the very first stars that formed in our universe, were they different from the stars that are forming today? And there's good reasons to believe that they are different because they're forming from a different chemistry. Today, we've got heavier elements mixed in with the gas. Back then, it really was just hydrogen and helium, right? And we've got good feelings that those stars would be very different. And then how was the early universe enriched with these heavy elements? And how much of that was locked up in dust? Right? Dust is important because actually dust is really tiny grains, forms the basis of planets like the Earth. Okay, and so these questions can actually only be answered through the synergy of state-of-the-art observations and modeling. And so that's what I'm going to talk about next, kind of how we do both of these things. Okay, so how do we observe the early universe? Well, I've kind of talked already about, if we just look further away, we're able to see back in time. So fundamentally, to observe the early universe, we just need to look as far back as possible. But actually, this is made really, really challenging. And this is for two reasons. So first of all, these very first galaxies are very, very faint, right? They're faint because they're far away, right? But they're also faint because they haven't had time to form very many stars. So we kind of have this double effect. They're faint because they're far away, and they're faint because they're intrinsically faint, okay? But this is compounded by the fact that we're seeing these galaxies when the universe was much smaller. And so because of that, as the light from these galaxies has traveled towards us, that light has been expanded in wavelength. So it's been shifted from visible light, which we can see with our own eyes, into the infrared. Now that becomes a problem because our technology isn't as good in the infrared for detecting that light, but also the Earth's atmosphere absorbs infrared light. And so it turns out to really explore this period of the universe's history observationally, you need a particular type of telescope. And that particular type of telescope is as big a telescope as you can make in space. Okay. And so, we really very much rely on the most powerful telescopes that we have access to. And today that really includes Webb, Euclid, soon the ELT, but in the past it was really Hubble. Okay. So a little bit about Webb. I'm sure people have heard about this a lot. This is this really wonderful telescope that was launched Christmas Day 2021. It feels like only a few months ago still, but equally it feels like we've had it for a decade. It's very odd. And just to remind you that this is our telescope. It's not simply an American telescope, right? So the European Space Agency, our space agency, was integral to this mission. In fact, we built the two most complex instruments and we launched the entire thing, right? The Americans, they just built the actual structure. That's the easy bit, right? We launched it and built the really fancy cameras. So it is our telescope. Now, Webb was, it was envisioned as a scientific successor to two other telescopes, Hubble, which I'm sure most people are familiar with, but also the Spitzer Space Telescope, which was a dedicated infrared telescope. But Webb, straight away is much, much larger than these other telescopes. It's around 6 times larger than Hubble, 50 times larger than Spitzer. But because it has much more advanced cameras, it is around 10 to 1,000 times better than either of these telescopes, depending on the wavelength of light that you're interested in. So it really, is transformational for our field. Okay. And unlike Hubble, Webb is actually designed to see the infrared. So it's designed to see this stretched light. Hubble, in the end, could do some infrared science, but it wasn't really designed for it in the first place. And in fact, unlike the other two telescopes, Webb has extensive spectroscopic capabilities. Okay. So ever since it's been launched, Webb has been conducting a large number of different surveys, both in imaging and spectroscopy. So imaging, we try and take an image of the sky, typically different wavelengths with different filters. And then spectroscopy, typically you'll target individual objects and then you'll get their spectrum. So you get the full information about how the light changes as a function of wavelength or color. Okay, so Webb's been doing both of these. So I'll just give you one kind of nice example of some of the imaging. This is one of JWST's deep fields. This is called JADES. And this is a really quite small patch of sky. It is, a couple of millimeters held at arm's length, right? So it really is a tiny patch of sky. And virtually every single point of light you see here is a galaxy containing hundreds of millions to hundreds of billions of stars. And these galaxies are stretched across almost the entire history of our universe. In fact, we can zoom in to this bit over here. So you can see more of these galaxies now. You can see some spiral galaxies. You can see the brightest thing there. That's probably a spiral galaxy we're seeing edge on. But I don't care about any of those things. I actually care about, and you would never guess which one I care about, it's actually this one. Turns out this little red blob over here is the most distant galaxy in the universe that we've ever discovered. Right? This is a galaxy that we're seeing when the universe was only a couple of 100 million years old. Okay. Now, I mentioned that we can also obtain spectroscopy. And what spectroscopy gives us for these individual galaxies is much more information. So what you're seeing here, and I admit it's a little bit of a small diagram, but you're showing spectroscopy of 3 very distant galaxies, right? So you can kind of see these noisy curves. But these noisy curves are punctuated by these emission lines. And in this visualization, you can see these emission lines are marked. Now, what you're seeing in a couple of these galaxies, in fact, all of these galaxies, are these emission lines corresponding to oxygen. Okay, so these, well, I think this has actually died. So these kind of blue lines are marking these emission lines of oxygen. And what this reveals to us is that these really early galaxies are already chemically enriched. Right? So these early galaxies already have things like oxygen, nitrogen, carbon. They already have, thank you. They already have the foundations for life. Okay, and this is relatively early on in the universe's history. So this straight away has told us something that we weren't sure about before. This is telling us that actually the universe becomes chemically enriched, chemically mature very, very quickly, right? Within the first couple of generations of stars. Okay. But Webb is not the only telescope in the game. Webb actually has some quite significant limitations. So Webb has this really small field of view. So at any one time, Webb only sees like this tiny fraction of the sky. So over Webb's entire mission, it's only going to cover a few square degrees of the sky, right? So, a few times the size of the full moon. So a really, really tiny fraction of the sky. And although it's much, much better than Hubble, right, these early galaxies, because they're still so far away, they still just look like a blob or a collection of blobs, right? So, we're still missing a lot of information here. And so augmenting Webb over the next few years, right, is a few more telescopes. So first of all, we have ESA's Euclid telescope. This launched a few years ago. This has a much larger field of view, right? So you can see its field of view compared to NIRCam over here. And this telescope, although it's a much smaller telescope, it's going to map most of the sky. Nowhere near as deep as James Webb will, but this will allow us to find the really rare, bright things in our universe. And that really nicely complements Webb. Okay. I think perhaps more exciting, because it's really big, is the European Southern Observatory's Extremely Large Telescope, which is the largest ground-based telescope which is under construction at the moment. This image of it under construction, this is actually from, I think maybe about 9 months ago now, so there's probably some newer ones. But for context, the ELT over here is about 40 times the collecting area of Webb. And that actually allows it to overcome some of the downsides of being here on the Earth, right? Because you're able to collect so much light, right? It doesn't matter if the atmosphere is absorbing some of it. And so because you've got such a huge mirror here, this actually allows you to look at individual galaxies in really, really fine detail. So again, the ELT is going to complement Webb, not replace Webb, at the other end of the scale. So it will allow you to look at individual galaxies in exquisite detail. And this should be ready over the next 3 or so years. And here's another image of it under construction at the moment. Anybody who knows Brighton, you'll know that this structure here is about the same size as the Amex Stadium there. So this really is very, very large. This is built on top of a mountain in the middle of a desert in a very remote area of Chile. So it really, other than just being a wonderful tool for astronomers, it is an engineering marvel as well. And this is a nice picture actually now looking down into the telescope, showing you the mirror, but without the actual mirror in place. So actually, very much like Webb, it will use a segmented mirror. So its mirror is formed of lots of hexagon segments, which are not yet actually in the telescope, but you can see the structure is there. Okay. So observations are really important, right? So they allow us to actually collect data, right? But we astronomers, we're not just interested in stamp collecting. No offense to any stamp collectors in the audience, right? We're not just interested in finding images of galaxies, right, or other interesting objects. We're fundamentally interested in actually understanding how galaxies form and evolve over time. The only way we can really do this is by comparing these observations with a physical model. Okay. So again, just reiterating this, observations give us clues about how the universe works, but it's not enough on their own, right? We really need models to do this. I shouldn't do this. This is ChatGPT. It's actually not quite that bad. I don't know why the people look so angry at each other. Yeah. So in the context of galaxy formation, what does our theory look like? Well, our models these days take the form of simulations, and these simulations are essentially fake universes or synthetic universes. Now, you can have other types of theory, right? So in some contexts, you can describe your objects, right, just by a set of simple equations. But it turns out galaxies are so messy in how they form, you need these big simulations. And so what I'm going to do now is just try and impart some understanding about what I mean by simulations here. Okay. So to do this, we're going to go back in time. We're going to go back to the really first simulations. These were run really kind of in the 70s and 80s. And these early simulations, they focused on trying to simulate relatively small chunks of the universe using very, very simple physics. So what they did in these very early simulations was say, I've got a chunk of the universe, a little box of the universe, and let's say that universe just contains matter, and that matter just interacts gravitationally. And then I know how gravity works, so I'm going to partition my matter in the universe into individual particles, and then I'm going to write some computer software which traces how those particles interact with each other over time. Okay? So we partition our universe into all of these little parcels of matter, these particles, and then every single particle tugs gravitationally on every other particle, but we can just do a loop over a loop, and we can actually see how these particles will move with respect to each other due to their mutual gravity. Before we do that, though, we need to decide where those particles are in the first place in our box. We've got our little box of the universe. If I just sprinkled those particles randomly in my box, actually nothing really is going to happen, right? Because if they're sprinkled randomly, the forces on each particle basically cancel out. And that's not how the universe works, because we see our universe today has structures in it, it has galaxies, it's got planets, it's got people. And so there needs to have been some kind of ordering of these particles or this mass when the universe first began. And so in the context of simulations, we say that we need to set some initial conditions. And this is really what was the initial masses, the velocities, and the positions of these particles. And we get this information from the cosmic microwave background. So the cosmic microwave background, which I alluded to before, is really a map of what the universe looked like when it was really young. And so the red spots in this map over here actually tell us where the universe was a little bit more dense than the average, and the blue spots are where it's a little bit less dense than the average. And we can translate what we see in this map into the positions of all of these particles, right? And so instead of sprinkling them randomly, we sprinkle them in a similar pattern, and then we press go. And when we press go, we get something like this. This is I don't know why it's so jittery, but we have a simulation here of our unit of, why is it doing that?
It's going over to you.
Ah, yeah, okay. Okay, yeah, it's very smooth on my computer. Oh, that's a shame. But what you should be seeing here is the universe started off relatively featureless, right? You couldn't see the differences in these particles, but over time, gravity enhances these small differences, these small inhomogeneities, and gives rise to this web-like pattern that we see today. It's a bit of a shame. Okay. So from these early simulations, what we were able to predict is that today, we don't expect the matter in the universe to be spread evenly throughout the universe. It forms this, what we call cosmic web. It's like a very filamentary pattern. And in fact, that is exactly what we see in observations. We don't see that galaxies are spread uniformly in space. They're kind of clustered together and they form all of these filaments. Okay. So these really early simulations, though, they were very, very crude. They only included one piece of the physics, which is gravity. Now, we know that our universe has much more sophisticated physics, right? And so over the last 10 years or so, we've been adding all of this richer physics into our simulations. So this includes the physics of things like gas. So gas can cool, gas can turn into stars, stars can blow up and return energy to the gas can form supermassive black holes. Okay. So in our modern simulations, instead of just having particles that represent mass, we now have particles that represent dark matter, black holes, stars, and gas. Okay, so we're now partitioning our universe into these four things. And the idea is that these four things can now interact with each other in ways beyond gravity. So this is a little bit of a complicated diagram, but this is just meant to show that there are different ways of these particles interacting with each other. So for example, everything interacts with everything else via gravity, because everything has mass in this picture. But for example, well, sorry, I just said that. But gas can form stars. So we have some kind of physical description that says if the conditions of the gas are right, we turn that gas into stars. Okay, so star formation. So this is just an excuse to show my favorite image. But we know that stars live and die, and when they die, they release energy and material back into the surrounding gas. And so we also have an arrow going back to the gas. So we have what we call stellar feedback. And again, an excuse to show a nice image, right? This is a star like the sun that has ended its life, and it's returning this material that we're seeing glowing at the moment to its surrounding gas. And that material might be recycled into a new generation of stars and planets. So for all of these interactions, what we need to do to build our computer model is write down equations or laws that describe all of these things. Okay. But once we do that, what we can do is we can take some initial conditions from the cosmic microwave background, and we can combine that with all of these laws. And I've written down some of the integral physics here. So gravity, hydrodynamics, which is how gas moves. The gas can cool, star formation, black hole formation, feedback, chemical enrichment, the formation of dust, and so on. So this is our model, combined with our initial conditions. And then we combine it with as big a supercomputer that we can convince somebody to give us access to. Right? And when we combine all of these things together, we can produce synthetic fake universes. And this isn't going to work because it's over Zoom. But what we would see right now is a really nice simulation of a galaxy forming in one of these simulations. Let me see what actually happens. Oh, was hopeful there. It's better than the previous one, but what you're seeing here in the main panel is the gas, and this is a galaxy which is growing, so you can see this gas is kind of collapsing down into the middle. And what you can see in this smaller panel here, right, is actually the stars in this galaxy, right? So the gas is being converted into stars. This is the dark matter on a larger scale. But in these simulations, we're seeing the formation of a galaxy here. Now, this galaxy at the moment looks kind of rubbish. It looks like a blob. But if I try and move all the way to the end of the simulation, we have actually formed a spiral galaxy in this simulation. So by putting all of this much more complex physics, right, and we didn't know that this would produce spiral galaxies, these spiral galaxies have emerged from these really, these simulations, right? In fact, these simulations work really, really well, right? They are able to reproduce most of the properties of the galaxies that we see in the universe. This is another one of these simulations. This one is actually, ooh, I'm not going to do that. This one actually has sound, but it's not going to work. So I'm not going to show it. It's a little bit wobbly as well. Okay. So I've talked about all of the background to my research. Well, what do? Well, my team, we run these simulations. So what you've seen is some of our simulations. And the main point of our work at the moment is actually we want to run as big simulations as possible. So we're spending a lot of our time working on more efficiently making use of our finite computing resources to build as big synthetic universes as possible. We also specialize in making synthetic observations from these simulations. We want to see what these galaxies would actually look like in our telescopes, because then we can compare them with the real galaxies that we see, and we can use that to test our models, right? And then we want to explain, well, in these simulations, we put in some physics, but lots of that physics is uncertain, and we can actually play around with the physics and run the simulation again, right, and see how it changes the outcome. So this is what we're doing a lot of times now. We're kind of updating the physics or exploring the physics. As I said, on the whole, actually, there's really, really good agreement between our simulations and the observations. So we're getting the broad details right. We produce kind of the number and diversity of galaxies that we see in the local universe, right? So this is tremendous progress. We're able to essentially make fake universes, right? Which we see galaxies and stars forming from relatively simple physical laws that we put in. But we've started seeing some discrepancies, okay? So in fact, there are two major tensions that we see with all simulations, not just our own. In fact, the universe seems to contain more dead galaxies than our simulations predict. So dead galaxies are galaxies which are just not forming stars anymore. And the universe seems to contain more supermassive black holes than our simulations predict. Now, it turns out these two things are almost certainly linked, because we know that one way of killing galaxies, stopping them from forming stars, is to grow a really big supermassive black hole in their heart. Because as you grow these supermassive black holes, the supermassive black holes release energy, and that gets rid of the gas and heats the gas up and stops it from forming stars. And so, in fact, we suspect that if we just update how we model supermassive black holes in our simulations, we'll be able to better understand or better predict these dead galaxies. And so this is one of our focuses at the moment. We're improving the black hole physics in these simulations to see if we can do better actually matching these observations in particular. Okay. So this really brings me to the end. There's a little bit afterwards. So just to make the point here that the James Webb Space Telescope has really transformed our understanding of the early universe. So it's really allowed us to actually probe all the way back to almost the beginning. So almost the very first stars and galaxies to form. Okay. Now, at the same time, we've been able to build increasingly sophisticated simulations that can reproduce many large-scale features of our universe. Okay. But some challenges remain. So the most recent JWST observations are really challenging, some of the details in these simulations. And so this is, good in a sense that there are still problems to solve, right? And so we're working on upgrading the physics in these simulations. And looking ahead, we're going to have all these new facilities that will allow us to continue testing and refining our models. And these include things like Euclid, Roman, the ELT, and the square kilometer array. These are all going to help us improve these simulations and really understand the physics. Just before I actually finish, I've done for many years lots of public engagement in different ways, although that's kind of ebbed more recently as I've moved into administrative tasks. One of the things that I really do enjoy doing, and I do continue to do, is creating exhibits. I really like making very hands-on things. I like talking to people individually. So we've done lots of festivals. This is us at the Goodwood Festival of Speed, which is kind of down the road and just outside Chichester. And this is us at a music festival and us at the Royal Society Summer Science Exhibition. In fact, I'll be returning to the Royal Society Summer Science Exhibition, which is in less than a month this year, contributing to actually 3 exhibits. So I really decided to do too much this year, but luckily I'm not leading any, so I'm just consulting on them all. This is a free science festival in London, right at the Royal Society's headquarters, which is a wonderful place just to visit, just off the Mall. Encourage you to go. It's great. They have like special nights where it's just for adults, where you can get drinks and look at the science. They've got days which are just for school kids, and then they've got weekend sessions which are really targeted at families. So it's a really fantastic thing to do. There's about 14 or 15 different exhibits, of which 3 are astronomy this year. I'm also a director of the Observatory Science Centre, which is the former home of the Greenwich Observatory when it left London. So this is, not very far away. This is just north of Eastbourne in the village of Hurstmanzoo. In fact, just over these trees, this is a really wonderful castle. This used to be the functioning observatory, but today it's a science centre. Again, anybody who's got small children or an interest in astronomy, I really encourage you to go there. Particularly because science centres like this have had a really hard time since COVID. We haven't seen numbers get back up to where they need to be. So as many people as we can as possible. But it's really great, there's all the old telescopes you can look at, but then there's lots of very hands-on things as well. Actually, much more so than the actual Science Museum in London. And then more recently, I've been partnering with a documentary company called Atlantic Studios to get into, well, they don't call it virtual reality anymore, it's extended reality via headsets. And actually, I was a massive skeptic of this technology until I started playing around with it. But we've developed some really, really cool experiences, both about black holes for Android XR, but also for the Apple device, where we've developed a free experience all about the James Webb Space Telescope. Right, both of those are free from their respective stores. I appreciate these devices are incredibly expensive at the moment, but the hope is that these are going to take off in the future. And there's just some nice pictures, and I'll end there and see if there's any questions.
Anybody got any questions?
Oh.
Let's go with Peter. He was fast. Spare mic over here. Okay.
You do want me to run over the mic?
That would be very kind.
Who's it?
In the first bit, we were talking about the heat going away from the galaxy. Where did all that heat energy go?
Okay, so it essentially gets turned into potential energy. So as the universe expands, it cools down. So you're turning that kinetic energy. So in this sense, it's really how quickly the individual particles are moving that is then getting turned into potential energy. So as the universe expands. So if you made the universe compress again, that energy would return to the kinetic energy or the heat. So it's just been shifted from one form of energy to another form of energy. So it isn't lost in any sense.
Thanks for the talk, Stephen. If I understood your simulations, you're extrapolating from the microwave background, which itself isn't homogeneous. So do we know what caused that original lack of homogeneity?
That's a great question. So we don't know definitively, but we have a very good idea. So when you look at the cosmic microwave background, exactly, you see that it's very lumpy, right? And in fact, the image suggests it's much more lumpy than it actually is. So actually, those lumps in the cosmic microwave background, they're, where you see the red bits, that's where the universe is about 0.01% more dense than the blue bits. So it's actually not very lumpy at all. They're really, really tiny inhomogeneities, right? In terms of where they come from in the first place, the best idea that we have is that it's a consequence of quantum mechanics. So at the extremely microscopic level, the universe becomes fuzzy, right? So we see these fluctuations. So okay, so another way of saying it, yeah, so quantum mechanics basically says on tiny, tiny scales, we have tiny fluctuations in the energy density of our universe. It is just a consequence of quantum mechanics. Now, this is a bit of a problem because those fluctuations in quantum mechanics, they're teeny tiny. They exist on really, really small scales. But these fluctuations that we see in the cosmic microwave background, they are things that turn into galaxies and clusters of galaxies today. And so the only way that we know that we could take those tiny fluctuations in quantum mechanics and make them into the fluctuations that we see in the cosmic microwave background is by invoking something that we call inflation. And this was a phase of the universe where the universe expanded really, really rapidly. Now, we don't actually have good evidence that inflation took place other than as an explanation for where these structures came from in the first place. But it does naturally explain these structures in a few other problems, right? If we allow the really, really early universe to rapidly expand in size and then just kind of expand a little bit slowly. So that's our best idea at the moment, but the evidence is circumstantial, right? It could be that there is another explanation, but no one's really thought of anything better. There are observations that we can potentially take in the future, which will definitively tell us whether or not inflation did happen, but we're not there yet. Thank you.
Thanks for the talk. In the various interactions mentioned, you didn't mention dark energy.
That's right. So, yeah, I also didn't mention what dark matter was. They're entire talks in themselves. So in these simulations, when we set up the initial conditions, one of the things that we need to decide is, well, how much of that matter is in normal matter, baryons, and how much is in dark matter, right? And we have good ideas about those proportions and the amount of them from things like the cosmic microwave background. We also have to build into these models dark energy as well. And so the dark energy that we build into these models is basically the simplest implementation of dark energy. So in the models, we basically have something which looks like dark energy, which is causing this accelerated expansion. Now, what you could do is you can look at alternative models of dark matter and alternative models of dark energy and run entirely new simulations and see what happens. And so people have been doing that as well. So at the moment, for the simulations that I do, because I care more about the galaxies and not the wider cosmology, I really just fix the cosmology. I fix the amount of dark matter, and I fix the properties of dark energy. But what we've seen actually over just the last year is that our very simple model of dark energy seems to be breaking. It looks like that dark energy actually doesn't quite evolve in the simplest way possible. It actually looks like it's a little bit more complicated than that. So one of the things that some of my colleagues are doing is updating the simulations to take into account this more complex form of dark energy. And we'll see what impacts that actually has on galaxies as well. Because that might well change what these early galaxies look like as well, which means we have to revise everything else. So at the moment, we essentially assume these things, right? But you don't have to do that. You can explore different versions. Right? But they are still ingredients in our models.
Just a quick one. How do you come up with the figure for the age of the universe, kind of from the Big Bang to the end of the Dark Ages? I mean, how do we know that that's sort of whatever it was, 137,000 years, or are we kind of guessing?
So nothing's ever a guess, right? But things can be quite uncertain. In terms of the actual age of the universe, so from where we are today all the way to the Big Bang, That is relatively well constrained by a huge plethora of different observations, including the CMB, including how galaxies cluster and things like that. The actual point at which we can see the CMB, that time is actually very well constrained. That is, we know that pretty accurately, much more accurately than we know the actual age of the universe. The time between the CMB and the end of the Dark Ages is actually very uncertain, right? We don't really know exactly when the first stars turned on, other than that it was probably within the first 100 million years. In our simulations, they turn on after around 150 million years. But if we change the physics in our simulations a little bit, that number shifts by actually quite a large number, depending what you do. And so that's one of the kind of knobs that we can play with. We can play around with the physics, and then we will get these stars turning on at a different point. So some of these ages are actually known quite well. Some of them are a little bit looser, and some of them, like that one, are actually, we don't have a good observational idea of what they are yet.
Hello there. I'm not sure if it's your department, but do you know anything about the latest number of exoplanets?
So I teach stellar and planetary physics, even though I work on galaxies, because we don't actually do very much stellar and planetary physics at the university. I think the number of exoplanets we're up to now is a little bit more than 6,000. And that's changed from basically 8 or 9 in the mid-90s to more than 6,000 now. I think that's roughly the right number. It's either 6,000 or 7,000, which is amazing.
Thank you.
Who's next?
I wondered if you could perhaps reflect on some of the surprises that we're seeing from James Webb, like little red dots and extremely well-evolved galaxies much earlier than we would have expected, and what the implications might be for the origins of supermassive black holes and things.
So it's a good question. So what I would say is that there's been a lot of sensationalism. So I actually talked about this in my talk to the group here earlier today. And so what you may have seen within the first few months of JWST coming out was claims that JWST has broken our understanding of the universe, it's broken cosmology. Actually, a lot of the most egregious claims actually evaporated. And that's because we didn't understand the telescope well enough, and people were a little bit careless with their data analysis. And also some people, they only compare their observations with one model, right, and not with our models. And it turns out our models do fantastically well in most cases, whereas other models don't do very well. But they kind of said, oh, well, just because we don't agree with this model means that all models are broken. So there was some very bad things happen there. I was very conservative, and that's because I work on both the simulation side and the observation side. So I was the ideal person who could counter all of these. And so I was very skeptical about any of these claims right at the very beginning for these reasons. We had small numbers. We didn't understand the telescope. However, over the last few years, we're starting to see these tensions emerge, right? So things like the little red dots are these unusual objects which look like little red dots because we're rubbish at naming things. But it turns out those little red dots are probably supermassive black holes in their formation period, in their first formation period. That's kind of the best explanation we have at the moment. And that's really exciting because we don't know how that happens in the first place. And the way that we put that into our models is very, very, very crude. So the fact we're now finding these things, it's allowing us to update our models. And again, like I said, we've started finding these large numbers of dead galaxies, but the numbers are still very small. It's really only a handful, and we want more than that to be really sure that something is going on a bit weird there. And so I would say a lot of those early claims were very sensationalist, and I think poor science. But I think we are now certainly starting to see tensions with all galaxy formation models, right? And that's kind of unsurprising to me because the way we model some things in the simulations, particularly early black holes, is very, very crude and not really physically motivated yet. And that's what's most exciting, I think, actually, the black holes, because that is the big question that we don't yet have the answer to.
Can you say again what a dead galaxy is?
So a dead galaxy is a galaxy which is no longer forming stars, right? So you're not actively creating new stars. And so what dead galaxies look like, they are basically the giant ellipticals that we see today. So they turn essentially red or yellow because they don't have any of the young, hot blue stars anymore. So they're galaxies where something has happened to the gas. Either it's been kicked out of the galaxy or it's been heated so high a temperature that it can't form stars. Because for gas to form stars, it needs to be cool and dense.
I'm just wondering how much you can use advances in things like machine learning and artificial intelligence to improve your models and maybe even improve the simulations.
Yeah, so it's a really interesting question. What I would say is that astronomers, we've been using machine learning since before it was cool. We've been using machine learning for a lot of things for a long time. We certainly use it to kind of optimize our simulations and our data analysis. Where I would say there's an interesting change now is the use of AI tools like LLMs to allow us to code a lot more efficiently. So most astronomers, they did a physics degree, they didn't do a computer science degree. And these simulations that we run are very, very computationally expensive. And so where I've seen the biggest gains with AI is simply allowing us to code a lot more effective. And actually, I can take some of my rubbish code that I know that works and give it to AI, and it will improve that code, it'll even document it, and it'll make it more efficient. And then I can check it still gets the right answers. So I'm now replacing kind of the computer scientists in my team by AI. I code up that I know that works, and then I can improve it using AI. It's kind of
simulations up, I guess, right?
Yeah, so we can start using machine learning to the simulations, but it becomes quite dangerous because depending what type of machine learning you use, machine learning will often add in extra noise that you really don't want. It adds in stochasticity, which in some contexts is useful, but when you're trying to do what we're trying to do, it often doesn't help. So we use it in some contexts, but in other places, it can be quite dangerous to use. But you know, as a community, we've been using machine learning for a long, long, long time.
More questions.
Yeah, 4 minutes. I've got a train that I need to run to, or else I get trapped in Guildford. Not that that's a terrible thing, but.
How reproducible are your simulations, or is it too expensive to find out?
Really, really good question. So in all of these simulations, you have to set, like, there is some randomness when you start it, right? So there is, you have to choose essentially a random number. And if you choose a different random number, you're going to get a different outcome. So in fact, some people have done some quite interesting studies where they've just said, you know, all of the physics is identical. I'm just going to choose a different random number as my seed, right? And they've looked at what difference it causes. And it causes quite dramatic differences, right? And so what we end up doing these days is that we do several different simulations with different random numbers, right? Because that gives us some idea about the kind of intrinsic scatter, the intrinsic kind of chaotic effects that we see in these simulations. But it's really kind of interesting stuff because there is then a limit to what we can trust from a particular simulation. There is this kind of an inherent uncertainty in any quantity because of this randomness that we have to put in. And actually, there's a whole load of really cool papers because scientists are really lazy when they choose their random number generator. And so you often have to set your random number using a number that you just put in yourself by hand. And you could set it to be like the date, but lots of people set that random number seed to be 42. And actually, people have done studies that have shown that this has actually had some undesirable effects. If everybody puts that 42 in, it's actually causing weird biases. This is not just in astronomy and physics. I did one of these days whether it's going to be replaced by 67. Okay, I'm glad some people got that reference because I barely get that reference. It is interesting though that there's really subtle changes that you make, it does affect things. All right, so yeah, if you switch between 42 and 67, right, you get a different universe out each time. Right? Statistically, they're very similar, but because of the noise, they're not quite the same, which is fun.
How do you gauge success in any one simulation?
Okay, so the question there was, how do you gauge success? The success for any one simulation is that we compare it to observations. And you can compare it to, you know, as many observations as you can. So generally, we compare it to observations of the present day, right? But then we can also compare it to observations of the early universe. So it really, you know, how well does it reproduce the universe that we actually see? At least on a statistical level, right? That's basically it. So how well have we done? Now, you could compare it against all observations, or you could compare it against a subset of observations. The reason why you might compare it against a subset of observations is that you might do a calibration process where you try and get one set of observations matching, and then you see if it still reproduces everything else in the universe. So that's an important process to do. Instead of trying to fit everything at once, you try and get one thing right, and then you see if it's got everything else right, because then your model has some predictive power. Whereas if you get it to get everything right first of all, right, maybe your model is just too flexible.
One more question then. Do we have any understanding of what happened to all the antimatter? It was theorized. It was created at the beginning of the universe. And does antimatter or the lack of it have any bearing on your modeling?
So that is one of the really big outstanding questions in theoretical physics, right? We know that something must have taken place which resulted in an imbalance between matter and antimatter. Because by all rights, if you set up a universe, you know, simply, they should have cancelled out. It's great that they didn't cancel out because we're here. There are ideas, but we don't have a firm understanding yet. But that's very, very much a question for the theoretical particle physicists in the audience or beyond. Not my area. Too much hard maths for me.
Any theoretical particle physicists? Well, Stephen, thank you very much indeed. That's a wonderful.